All right, we'll finish up the nuclear notes about the nucleus. We're talking a little bit about chemical and nuclear reactions. We're going to specifically focus on nuclear reactions and where they happen. Okay, nuclear reactions happen all the time. We'll talk about the different types in just a minute. We're actually really interested in nuclear reactions because with nuclear reactions, we can start to study the building blocks of all matter. And that's important to us. We want to know what matter is made of. So scientists have built bigger and bigger and bigger, really, really expensive, important, essentially laboratory experiments. They're entire laboratories themselves, really. These laboratories are called particle accelerators. That is not the marker I was using. That's trash. There we go. There we go. Slightly better. Particle accelerators. Okay. They actually don't have to be very big. My college, Geneseo, had a particle accelerator in the basement. Couldn't fit in this room. Okay. Obviously, it's not as high energy as some of the big ones. You might have heard before of something called the Large Hadron Collider, or LHC. That is at a laboratory called CERN. The LHC is so big that it actually is, it's in the shape of a circle, and that circle goes under two different countries. It goes under the border of France and Switzerland. It's got a diameter, this giant tunnel, of about, I think, 20 or so miles. I could be a little bit wrong on that. It's approximate size. It is huge, and that's where some of our most important scientific experiments right now, in terms of doing nuclear science, nuclear physics, and figuring out what the building blocks of matter are, that's where a lot of them happen, at this place called CERN in France and Switzerland, in a big experiment called the LHC, the Large Hadron Collider. The way a particle accelerator works, any of them, they use very, very big electric and magnetic fields. They use these huge electric and magnetic fields. They take particles that would be in the nucleus, nucleons or even electrons, anything will work, and they accelerate them around. Okay? If you have a circular lab, you accelerate them around so they get going really, 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 really fast, and then they make them collide with one another. Okay? It's like gladiator fights, but for particles. They smash them into each other and cheer them on. And the reason they smash them into each other is because they want to see what happens. Nuclear reactions are not like normal reactions. Okay? They don't act just like regular collisions. For example, if I take two tennis balls and I throw them towards each other and they collide, I just get two tennis balls out. Okay? Two tennis balls rebound out of the collision. Now, if I throw them really fast, maybe like one of them gets a tear in it or one of them bursts or something like that. But you're not getting weird. Even that's expected. With nuclear collisions of particles at this size and this energy, you get really weird stuff out. Imagine taking those two tennis balls and colliding them, causing them to collide, and you get out not two tennis balls, but a baseball, a ping pong ball, a football, a basketball, a soccer ball, and maybe for good measure, like someone's shoe. Okay? That's the best analogy I have for what is happening at CERN. We collide certain particles, we get other particles out, stuff that wasn't there to begin with. Okay? Instead of getting particle fragments, the energy of the collision will actually create new particles that were not present beforehand. This picture is kind of like a readout of one of these collisions. It doesn't show, I can't read it and understand what's happening, but this is a computer-generated image, and a scientist who works at CERN studying these collisions would be able to tell what the different particles that are coming out of this collision are, just based on their arcs and which way they're going. And they can tell, oh, that was a new particle that got created. Ooh, that's a rare particle that got created. Okay? I'm hand-waving through this. I'm not really explaining a ton. I'm just giving you the facts because the details behind this are so complex. You need PhDs to understand this stuff. Okay? To really, really get it, you need to do years and years of research. I'm just here to tell you that this sort of stuff exists and is real. Let's go to something a little bit more manageable. Let's talk about nuclear reactions that are used to provide energy for us. We know of two types. We know that there's nuclear fission and there's nuclear fusion. Okay? They're essentially reverse processes. The current one that we know how to use is nuclear fission. Okay? When you use fission, you are taking something big and breaking it into something small. Just like this picture right here. You start with U-235, that's an isotope of uranium. You fire a neutron at it, neutron gets absorbed, it gets taken into the U-35, becomes U-236, excuse me. That is an unstable isotope. That will break down into two waste products, some krypton and some barium. Releases some neutrons. It also releases some energy, okay? When you do this, it actually releases a little bit of energy. That's why we use fission to provide energy. It's splitting apart of something very heavy into something smaller. We can build power plants around this idea. The drawback is, now I've got barium and krypton sitting around. And if fission worked differently, if it made products that we could use, it would be great. But it doesn't. These products are dangerous. These are dangerous waste products. We don't need them around. We don't know what to do with them, though. We can't really use them for anything, and they're hazardous to human health. So fission, the reason you hear about bad things happening with nuclear power plants, with our current ones, is because they generate a lot of waste. Chernobyl, okay, nuclear power plant in Ukraine, went into essentially a meltdown, okay? The nuclear reactor destroyed itself and everything around it. You still can't go back to Chernobyl today. There is so much radioactive waste there that you get sick almost instantaneously from getting too close to that place. It's not somewhere you want to go, okay? Fission creates waste products we don't like. That is why we are constantly trying to figure out how to actually start and keep going nuclear fusion. Fusion is the opposite of fission. You take light elements and you smash them together to form heavier ones. And believe it or not, this also creates some energy. It releases energy, I should say. It doesn't create it. It releases energy. Okay? But it happens without harmful waste products. This is the reaction that we saw in the front. You take some hydrogen, smash it into a different type of hydrogen, you get helium and a neutron out, you also get some energy out. It releases energy. This is actually how the sun powers everything. This is how the sun generates its energy, by undergoing nuclear fusion. We know how to do nuclear fusion, okay? We know how to get the reaction going. We know how to keep it going. Currently, we just can't start fusion without using way too much energy in order to start the whole thing. We have to put too much energy in as opposed to what we get out. If we ever get to the point where we are putting less energy into fusion than we are getting out, now we've got something important. Now we don't even really have to worry about energy ever again. Okay? Nuclear fusion can solve all of our energy problems if we develop it enough. There's one other type of nuclear reaction that I want to talk about. Not fusion or fission, but something that you studied last year, and that would be radioactive decay. Okay? Radioactive decay happens when you have certain isotopes or certain versions of elements. Okay? Isotopes of an element have the same number of protons, however they have differing numbers of neutrons. Some isotopes, some elements with some certain number of protons are stable, meaning they'll be around for a while. Some are unstable, meaning they change into other things spontaneously. And when that happens, we say that the object is undergoing radioactive decay. They spontaneously emit either particles or radiation or energy. And when this happens, they actually change into a different isotope or element. Okay? You studied this last year. I'm only bringing this up now because this phenomenon of radioactive decay is controlled by another fundamental force that we have not talked about yet. We just talked in the last video about the strong nuclear force, holds protons and neutrons together inside the nucleus. Well, if there's a strong nuclear force, why do we have to call it the strong force? Because there's another force that's inside the nucleus. And by default, that one has to be the weak nuclear force. The only thing you have to know about the weak nuclear force, it's weak, it's in the nucleus, and it is responsible for radioactive decay. Okay? This force does not work outside the nucleus, it's very weak, and it controls radioactive decay. That's all you have to know about it. So if you hear weak nuclear force, you immediately think radioactive decay. And at this point, I'm going to change topics one last time. And we're going to talk, now that we've talked about the weak nuclear and strong nuclear forces, we're going to talk about what are called the 4 fundamental forces in physics. Any force that we have learned about this year, okay, whether that's the spring force, tension, normal force, gravity, applied force, friction, any of those forces, you can categorize them in one of 4 different ways. Okay? We have what's called the strong force. We have the electromagnetic force. We have the weak force. We have the gravitational force. With the exception of the force of gravity, the weak force, which we just mentioned, and the strong force, every other force you guys have talked about this year is somehow an extension of what is known as the electromagnetic force. The electrostatic force is a great example. That's forces between charges. But what about friction? Well, friction arises because the particles in your hands, they have charges, they have protons and neutrons. When those protons and neutrons and electrons slide over each other, there are some electrostatic forces that arise. Friction is actually an electromagnetic force. The applied force, or the normal force, when you were in contact with something, you are not really touching it, you are just getting your particles so close to the other object's particles that there's a really big electrostatic force repelling you. Okay? I always give the example, when you're a kid and you're messing with your little sibling, you're saying, I'm not touching you, I'm not touching you, I'm not touching you. Even if you touch them, you're really not touching them. What you are feeling is the repulsion of the electrostatic force. It's just so strong because you're so close to that object. You can never actually touch something else. That's really weird to think about. I'm losing my point. Any force besides the force of gravity, the weak force and the strong force, they are all derived from the electromagnetic force. The only separate ones are the strong force, weak force, gravitational force. Where it says relative strength, we're going to put them in, they are in order. The strong force is the strongest. The electromagnetic force is pretty strong. The weak force is pretty weak. And surprisingly, the gravitational force is actually the weakest. Gravity only becomes a factor when you have huge masses, okay? When you have really, really, really big objects. I'd say something along the size of like a small hill, okay? Or a large hill, I should say. That's when gravity really starts to have an effect, okay? The range of the force, strong and weak, are simply inside the nucleus. They don't work outside of it. The electromagnetic and the gravitational force are a little bit different. Both of those forces are proportional to r squared. There's an r squared, or 1 over r squared. There's a 1 over r squared in the bottom of each of those equations, which is really strange. You can make the distance as big as you want. That force will never actually get to 0. So the range of these forces is actually infinite. Gravity still works if you are really, really far away. It's just very small. Same thing for the electrostatic force. Okay? Now, real quick, what do all these forces do? The strong force holds the nucleus together. Holds nucleus together. The electromagnetic force holds small objects together. Humans are held together by the electrostatic or electromagnetic force. Houses are held together by the electromagnetic force. The range where that stops holding things together is, like I said, the range of about like a small or a large